So first, two announcements. So first of all is that tomorrow there will be only 2 talks. So the most up-to-date schedule is on the internet, so on the website. And we will start on, so as usual, so at 9:30, so 9:30, 10:30, and then 30 minutes break, and then 11 to 12, so as usual. And then, yeah, so Thursday and Friday is as Monday, Tuesday, so 4 talks. So 2 talks in the morning and 2 talks in the afternoon. And the second announcement is that we will make the group photo. So after the end of the first talk this afternoon. Yeah, so please, after the first talk, please still stay here. So we will take a photo from there. Yeah, inside, yes. Okay, thank you.
It's my pleasure to introduce Stephen Liu, Professor Stephen Liu, who will talk about multiple fiber of Lagrangian fibred hyperkahler varieties and antihyperbolic results. Thank you very much.
Well, I first would like to thank the organizers for inviting me to such a wonderful conference. And also, it has been a very long time since I've been traveling. This is after 4 years. Back to Taiwan. It brings a lot of memories, and I see a lot of old friends. Actually, I'm here to tell you basically a very old story that started with the case of surfaces, and now has evolved into a big study on Lagrangian varieties. I mean, I'm not a specialist on hyperkahler manifold or Lagrangian fibrations on hyperkahler manifold, but I will be talking to you about them today. But really the story is no different from the surface case. So I'll actually focus a bit of time on the surface case first and tell you why, from the introduction, the motivation, and so on, why this is interesting. And hopefully in the end, you might agree with me. So even though this is a conference in birational geometry, algebraic geometry, I'm coming from a perspective from hyperbolic geometry, more transcendental object. So I'll give you some review of those concepts. So I'll start with a compact Kahler manifold. Usually, and in fact, always assume that this is. In fact, later on, I will generalize the notion to Kahler varieties with rational singularities. So recall that we call X to be meromorphically or holomorphically dominable. And sometimes I'll just use the word dominable if there exists a either holomorphic or meromorphic map from some affine space Cm to X, with the condition that the map is surjective at the origin. Okay. The differential, okay, it's surjective. And in fact, we can, in all the examples that I'll talk about, you see that there's no problem for me to actually also add the condition that this is true, that this will be true, also hold for all P in X. And there exists such an F with FP. So in fact, once you know that it's dominable, in fact, you can have this condition of dominability at every point on your target space. So the remark. So this condition, I mean, you can think of it as a transcendental analog of being unirational. Okay, but it's actually more than just unirational. Because dominable implies, for example, if it's dominated by a abelian variety, it's also dominable in this sense, right? So a few remarks. You can take M equals N. Okay, that's clear by taking sections, linear sections in CM. Condition B implies condition A. So if it's a holomorphic dominable, of course, it's paramorphic dominable. But in fact, the converse also holds. Okay. Converse holds in all known cases. Known cases. And if X is of genotype, then a genotype variety implies that there exists a degenerate volume form on the canonical bundle. Okay, and if you take the Ricci curvature or the Chern form of this degenerate, possibly degenerate metric, this would be bounded below by epsilon times omega. Okay, so this is a hyperbolicity. Volume hyperbolicity condition. Okay, so this implies by the usual Schwarz lemma, all for Schwarz if you like. It's the maximum principle that X is not dominable. Any questions? So, I mean, there are people who ask me why one should be interested in hyperbolic geometry in the study of algebraic object. And one of the reasons I could give, okay, I don't know for one of the first reasons, is that when you have hyperbolic geometry, so something is negatively curved, so you have the Schwarz lemma applies. Okay. So Schwarz lemma means what? It means either distance decreasing or volume decreasing, right? Property. So when you have those type of property, you get some sort of compactness result, right? If you have distance decreasing, you have equal continuity of a family of maps, and therefore you have compactness result for family of maps. Okay. So boundedness results comes naturally from hyperbolicity conditions, and in fact, a lot of finance results, whether in the sense of moduli spaces or in the sense of varieties, they can always be reduced to questions about hyperbolicity in some sense. So I'll be giving another talk in 2 weeks here in Taipei in a different conference, which is more related to hyperbolic geometry. There I'll talk about why the Schwarz lemma or the sequence property is very useful for many, so boundedness result. If you have rigidity, then you get finiteness result. Okay, and that's very often the case. The rigidity is actually built in very often in the case of hyperbolic geometry. So whenever you have dominability, that implies obviously there exists dense, in whatever sense you like, entire holomorphic curves. Entire holomorphic curves. So what is an entire holomorphic curve? And let's just take one. That means this is the holomorphic map from C to your X. Sorry, from complex plane to your X, such that the closure, okay, there is a closure or topological closure is equals X. Whichever topology you choose, you can find such an object. Okay. And it actually also implies also that this is a canonical invariant metric associated to X. It's called the Kobayashi. Some people write Kobayashi or hyperbolic, whatever. This is, and very often people just omit that. Or it's infinitesimal metric, infinitesimal norm on the tangent space. So this is a Finsler norm. So this object, these objects are identically vanishing. So this is this is called the Kobayashi pseudometric. This is the Royden infinitesimal volume form. So they vanishes identically. Vanishes. All right. So, this condition of the Kobayashi metric being vanishing is somewhat analogous to, for example, rationally connected varieties, right? Or, so example, analog of the condition of being rationally connected. Okay. And but this is also true. So vanish identically, this is also true for elliptically connected. Not just rationally connected, but connected by abelian varieties. I don't really know whether this is a good choice of word. This means chain connected by abelian varieties. Or in more generally, if you are in just the Cater context, by just Cn quotient by gamma, compact ones. Okay. So a conjecture of Campana and many people have different conjectures. So I believe we were the first ones to make such a bold conjecture. Campana around the same time, myself. So X being special, so I will not go into the definition of being special, okay? So special just means not general type, okay? For example, it means not general type, okay? But if you say, so basically you can think of special as being far away from general type, okay? Not just not general type, but far away from general type, okay? As far away as you can, you see.
Greater dimension.
What?
Greater dimension is small.
General type, you mean?
General type is maximal, but special means that greater dimension is small, right?
No, the quadratic dimension could be the only special only eliminates the genotype condition. So special implies not genotype, but any other quadratic dimension is possible. Okay.
One direction.
Only one direction is true. Okay. But if you change not genotype to very far from genotype, then that's more or less the meaning of just special. Okay. So this condition of being special is an algebraic condition. Okay, it's a birational condition. And its conjecture says that this should imply some or all of the above properties. Okay, I'm going to call them antihyperbolicity. Antihyperbolicity properties. Okay, so this is antihyperbolicity means as far away from hyperbolic as possible. Okay, antihyperbolicity condition properties, okay, or conditions. So the converse of this conjecture are mostly either trivial or it's not hard. Okay. Now I'm going to concentrate on the surface case. And I will assume, because these are all birational notions, I can always assume that X is minimal. Okay. So in this case, X special implies that X is P2. Actually, since we're we're working over C, it's a Cater manifold. X is C2 ruled C2 quotient by gamma. Okay. So it's not just usually ruled. This is all ruled over a curve of genus less or equals to 1. Okay. So this rule just means it's a Connet model over a curve of genus less or equals to 1. That's the condition on the genus comes from the fact that X is special. Okay, this cannot be genotype. Okay, genotype curve or have genus greater than, strictly greater than 1. Okay. So these are evident in the nominable. Okay. Now, the elliptic surface and K3 surface are not that evident. Okay. There are two other cases, elliptics or K3. Okay. So these type of elliptic surface, that means that there exists an elliptic vibration from X to a curve. And again, because of special condition, not genotype, the curve is has to be not a genotype. Okay. But it's actually more than that. So, and the general fibers, generic fibers elliptic curve. So that's, because this conference, we talk about higher dimensional generalization of this for elliptic K3s. They're called Lagrangian fibred K3s. So this theorem I worked out with Greg Buzzard. Actually, we did this in the mid-90s, but we couldn't, we want to actually cover the K3 case. And we just sort of left the project for a while, and we try to work on different things. And in the meantime, we discovered, for example, that dominable implies that it's actually, you can actually avoid, holomorphically avoid codimension 2. Okay. So that gives us hope that in fact, we cannot only deal with elliptic, but maybe with all of K3, because elliptic K3 ones are actually dense in the space of K3, right? In the moduli space. Any Kodara dimension 1, for example. And Raker surfaces are all elliptic.
Yes, they appear.
Yes, they appear here, of course.
Any surface.
Yeah, any surface. Yeah. This is an exhaustive list for special. But it's not mutually exclusive, at least even birationally. So this is was published in the year 2000, although we did it in much earlier. So special elliptic surfaces are dominable. In all the senses that I talked about. And also because we didn't want to give up at the beginning, we want to treat all the case threes, we actually proved that we can actually, for dominability, we can even get rid of codimension 2, actually a neighborhood of codimension 2 subset. Okay. So you have A implies B. So for all non-dominable. And in fact, for all non-dominable, X, okay. For all such X, in fact, for all finite set, there exists a neighborhood V of S such that X minus this neighborhood itself is holomorphic dominable. Yeah. And it's not just in dimension 2, it's actually higher for higher dimensions as well. Okay. For projective space minus, for example, any codimension 2 subset is dominable. Yeah. Yeah. CP2 is not, you mean whether it's dominable or not? Well, CP2 minus a line is C2. Yeah. Any line. Okay. You can go. Okay. Right. Yes. Any case, any case 3, not enough. In fact, we don't even require a projective. We don't even require Kahler. Okay, for surfaces, it's fine. It's all locally projective. Okay. The elliptic ones anyway. So one interesting fact. So let me just write this for the sake of completeness. So this implies the two-dimensional dominability conjecture above. If it holds. So the only case that we cannot deal with is X equals non-elliptic non-Kummer case. So those are, so if it's elliptic or if they're Kummer, then by construction they're dominable.
What's the idea for this?
Yeah, I'm coming to that. Yeah. So X is elliptically this is just a remark, this connected if projected case 3. Okay. So for projected case 3, they're elliptic connected. This is a paper by Mori Mukai. I don't remember the time, is it 83, something like this? This is an observation of, well, in the paper, they said it's an observation of Bogomolov and Mumford. So in particular, this implies that, in fact, let me call this star, the two-dimensional dx conjecture holds for projective non-general type surfaces. So unfortunately, for general type surfaces, we don't know whether the Kobayashi metric vanishes identically. Okay. So this is an important conjecture of Serge Lang, and he actually claims that the Kobayashi metric does not vanish on a Zariski open set. Okay. So that's this, still an open problem even for the case of surfaces, and very little is known. Okay. Very few examples of general type surfaces we know this, okay, except very simple, except for very trivial construction for very trivial select product and so on. Okay. So, sorry. So, for the elliptic ones, let me give you an indication. Okay. Indication to prove. So if you take a elliptic vibration, that means, as we all know, there exists a Q divisor, orbifold divisor, delta sigma, is 1 over MP, E, just sum it over P belongs to C. So there's a Q divisor on C, such that the pair, it's an orbifold pair, delta, let's call it, is a special orbifold. So in the case of curves, special just means not general type, okay? Special, not general type, or not hyperbolic, okay? General type is the same thing as hyperbolic, large dimension maximum, 1. Then it's a special orbifold curve. So there are many characterizations of special, or if you use Gauss-Bonnet, okay, negative curvature means that the order characteristic must be negative. Okay. So you only left with the possibility that the degree of the pair, of the canonical bond of the pair, which is by definition the orbifold order characteristic of your orbifold, greater or equals 0. Okay. So the orbifold order characteristic or the degree, you know, from Riemann-Roch or whatever you like, this is the minus degree of delta. So this is equivalent to this condition. What? Pardon? Strictly larger. No, just equal. Larger equals to special. Yeah, you can have flat. Flat is special. Only negative curved is not special. Okay. So if the tangent bundle is trivial, the orbifold tangent bundle is trivial, then then of course this degree is 0. That's the case when it's special. Okay. So special includes both P1 and elliptic curves, right? Only hyperbolic is not special. So non-hyperbolic means special. Right? This is if and only if in the case of curves.
I can take delta equals 0. So it's the
Yeah, you can take delta equals 0.
Where this and so delta is associated with x, not with c.
Delta is a Q divisor on C. You sum it over points in C.
Have to do with x.
No, has nothing to do with X. So anything associated to X cannot be a genotype. That's the notion of being special. Okay, so in particular, this object C, including with the structure or orbital structure that comes from this vibration, has to be not genotype. Okay, that's the meaning of special, right? Yes. I'm sorry, did I get this wrong? Degree of minus kx. I'm sorry, this is degree of the tangent bundle. That's the only characteristic. Sorry, yeah. Okay. So then for the second remark in the corollary, that we can avoid codimension 2 subset. Okay, so avoiding neighborhood of points of codimension 2 uses the existence of feedback domains. Feedback. So these are objects which are embedded holomorphic images of C inside your Stein object that one deals with in this problem. So basically, in the proof of this, I haven't finished the proof. You want to go to the universal cut. You want to pull back this vibration to some sort of a covering of on C, which to remove the multiple fibers. Okay. So you want to do a finite base change by this orbital structure to remove the. So in order to do that, you need to have a uniformization that kills all the multiplicity. Okay, you cannot do that in general. Okay, but the only case you cannot do that is if C is equals P1. Okay, with some finite number of possibilities. But if you eliminate 1 point from P1, then it has a universal cover, which removes all the multiplicity. So the universal cover in that case are all C. Okay, so there exists so anyway, there exists feedback domain images embedded images of C2. Okay, inside your Stein surface. Okay. And this Stein surface is usually a universal cover that we'll talk about. So you pull back the C. So you do a base change, you get a Stein your Stein object. Okay. Anyway, over a Stein curve. Okay. In this case we actually deal with the Stein curve. Okay. That's the base. So in any case, given an arbitrary vibration, so this is I'm continuing this proof, but just making a remark that this remark probably I should have done a bit later, but actually the whole gadget will work, even though I haven't finished the indication of proof, if you have, instead of elliptic vibration, an abelian vibration will occur. So if the fibers are, if the generic fibers are abelian varieties, the same thing would work. And why is that? Well, let me give you quickly how that works. So I already mentioned how that works. Basically, you do so this implies that there exists, if you remove a point from C, there exists a universal cover, which is of this orbifold, okay, where C0 is actually your curve, or C minus a point. So now we base change, then base change. We get a vibration, elliptic vibration over C. Over C. And then this elliptic vibration will be no multiple fibers. Okay. Now, at the time I wrote this paper with Buzzard, we just checked the Kodaira's table of singular elliptic fibers. And we saw that, in fact, the GCD for the multiple fibers is the same as minimum multiplicity. So, but this one can prove directly, okay, even for abelian vibrations. So in fact, the multiplicity happens to be, if there are no multiplicity, that means the inf of the multiplicity on the component of the fiber is 1. So that means there's a component with no multiplicity. And what that means that locally there's a section through that component. Okay. So this implies there exist local analytic sections, okay, holomorphic sections. SI over UI inside C of this restricted vibration or the pullback vibration, sigma hat. So this elliptic vibration over C, I'll call this sigma hat. Okay. So it's sigma hat UI. UI. Of course, this section SI is just a section of SI. Okay. So we can choose a covering, a countable cover, an open cover UI with sections of this sort, such that on the intersection of these UIs, they do not touch the degenerate locus, the discriminant locus of your vibration. Okay. So in that case, once you have a section, then you can use the theory of neural models to allow you to conclude that sigma I restricted x hat delta I0. This mapping x hat I. So this is our x hat I. You can actually take away some components of the fiber of some fibers to make sure that this actually is a abelian group scheme. So a abelian group scheme comes equivalent to the section. Okay, that's the section that SI defines your abelian group scheme. Okay, yes, then abelian group scheme UI. So this sort of observation is general, okay, even for abelian vibrations as well. Okay. So once you have this fact, you can actually once you have a section, okay. So the section, so you think of that as the origin of your group structure on each fiber, okay. And you take the relative exponential map at this zero, okay. You take the relative exponential map, that will give you a map, a fiber space. Since these UI are Stein, this would be a trivial holomorphic product, and you would have a dominable map from there to there. Okay, so this you can obtain. So this C here, C cross UI, you think of this as the relative tangent bundle, the SI of XI hat over UI. The relative tangent bundle and restrict to the SI. Okay. So this would be exactly C cross UI, because UI is you can take the UI to be both the disk, for example, each UI, and then this would map to XI. Let's reject. Any questions? And but this SI is just one section in here, okay? But the SI corresponding to different patch, different UI. The other UI may intersect this, UJ may intersect UI. And SJ would define your section in here. But you can solve the Cousin problem to patch all these sections, okay? So this implies SC Stein. So H1, the holomorphic H1 is 0. So that means you can solve Cousin 1. The classical Cousin 1 problem to get a global section. S of sigma hat. So again, this implies that you get a domino map from X 0 to C to X hat. It's a rejected map, okay. Actually, of course, you have to take away some component. You just take the component on the fibers that corresponds to the section, okay. And this would be a domino map. So this is inside X hat. And this, of course, is the relative tangent space at the any questions? So all this, I mean, it's very clear that all this should also work in higher dimensions, right? But only if the base is one dimensional. So the theory of neural models, all right, did I mention neural models? Yes. What? Right, the theory of neural models actually works for one-dimensional base schemes, one-dimensional base. I actually don't know any theory in higher dimensions, but at least it works in codimension 1. So in higher dimensions, of course, you still want to exploit the same strategy. And everything would work. So let me tell you how that would work. Yes. Oh, yeah. I said it, but I'm not going to write it because I don't think I have enough time. I started at 2. Yes. Don't have enough time to go into higher dimension much. But once you have dominant map, you have all the other conditions of antihyperbolicity, including vanishing of the Kobayashi metric, right? And we were able to, me and Buzzard, were able to treat the projected case, but in a non-projected case tree, we couldn't say anything about the vanishing until 2015. Misha Bezvesi and Ludmila Kamenova and I used Misha's ideas of ergodic complex structure to show that, in fact, all case trees have vanishing Kobayashi metric. Okay. So that finishes that story for the case of surfaces. And of course, that idea applies to all hyperkahler manifold, okay, in higher dimensions. Not all hyperkahler, but all known hyperkahlers. So basically, once you know that if you have one hyperkahler with, say, a nice structure, let's say a double fibration, okay, a hyperkahler manifold with 2 Lagrangian fibrations, which are non-parallel, okay. Then it's the same idea. So you just use this. So you have a Lagrangian fibration with a multi-section, which is given by the other Lagrangian fibration, right? You know, Lagrangian fibration, then there will be a multi-section given by another Lagrangian fibration. And that multi-section you can base change by that multi-section. Okay, so that multi-section would be a abelian variety. Okay, so you base change to that abelian variety, you get an abelian fibration over an abelian variety, and therefore you apply the same method that I talked about before. So, because of lack of time, just let me mention to you how that works. So we know how to avoid codimension 2, okay, even for higher dimensional base. Okay. So we know that original fibration over your base, which is supposedly projected space, okay, though that's a conjecture, but at least it's some final variety. So that final variety may come with some orbifold structure. Okay, so as Mirko mentioned, that the base orbifold for this Lagrangian fibration in general of a hyperkahler manifold has to be a log final variety, okay, log final pair. It cannot be Calabi-Yau, okay, like it rules out the Calabi-Yau. You can rule out the Calabi-Yau case very easily, but yeah, that doesn't unfortunately give you much, still much to say about the possibilities. Okay. Mirko already mentioned there are only finite number of possibilities, and in fact, using bounds on the multiplicity by Oguiso and Juan, the multiplicity cannot be greater than 6. We know there are only finite number of possibilities, okay, for these log final pairs as the base. And in fact, in 4 dimensions, this is very special. Okay? In 4 dimensions, we actually know not only more or less all the possibilities, we know that the base is actually a Denny-Mumford stack. The orbifold base is not just it's locally it's always a quotient by a smooth finite. Locally it's always uniformized by C2. Okay, so that's the 4-dimensional hyperkahler manifold case. Yes, but for the story for hyperkahler manifold, you know, people there's really so much not known, okay, in general for algebraic in the terms of classification theory in birational geometry. Even in the case of hyperkahler manifold, okay, even though we know some boundedness result, okay, for example, four-dimensional hyperkahler are bounded, but we don't know very much beyond that. Okay. There are many cases. Most of the cases we cannot eliminate. So on the other hand, in the case of Lagrangian fibred four-dimensional hyperkahlers, we can be very, very specific, okay? Because we know that the base is smooth, therefore it's P2 by one's result. And anyway, the story of that the base is smooth is quite, it's a bunch of people that who are not here, I think. So I don't have to mention them. Oh, they may be it's recorded and they're on the internet, yes. But we all know who they are, okay. They are famous people. So one of them actually had collaborated with me. So this is why I'm not mentioning the names, okay. Yeah. So higher dimensional case. So I have to quickly give you some. I don't know whether it's really meaningful to go into the singular case that much, but in order to deal with the general case, you have to treat a singular case. The general known case that we know, we somehow have to treat the singular case. So I'm just giving you the definitions here. On so higher dimensional case of hyperkahler. So this may be singular. Okay. So I'll just use the definition that Mirko gave. Okay. So we always assume that X is Q factorial for simplicity. And also KLT. You can always take Q factorialization, at least in the projective case. Okay. So, so a rational Lagrangian fibration on X is a rational map to some base. And this base, we know by Matsushita's result, this base is always Kahler. And in fact, it's Fano, KLT Fano. Yeah. With connected fibers. Actually, for what I mean by KLT Fano, I would like to put in at least a pair. Okay, that was talked about by Mirko. So with connected fibers, with general fiber, a Lagrangian subvariety. So Lagrangian subvarieties are we already mentioned in this previous talks. They're maximal with respect to the holomorphic symplectic forms. Okay, maximal holomorphic symplectic form identically 0 on these when you pull back. And if smooth, okay, so if these Lagrangian subvarieties are smooth, then we know that they're abelian. Okay, equals abelian variety. smooth. This is a abelian subvariety. If it's we know that it's smooth. Okay. So knowing that the abelian varieties is nice because we know that they have vanishing, they're dominable, they have vanishing copiability, they have all these nice properties, okay, that we want to use. So we will always assume, at least I will not, I guess I should write this down, but I'm not going to write it, that this is induced by some line bundle in the Picard group. Okay. Okay. That's it. So induced by A and L in the Picard group of X. This is not automatic, by the way. Okay. With some strong assumptions, well, for example, with these type of assumptions, you might get somewhere near. So induced by some L, it means that this map, this rational map, is induced by some high multiple of the linear system of L. Okay, the linear system corresponds to L. Okay, so one key lemma. I don't know if I have enough time to do this. No, I don't have enough time to do this. Let me just say that a result of Matsushita was generalized to the setting of singular hyperkahler manifold. So they actually Christian Land calls it primitive symplectic varieties. And he studied this systematically with Baker on the moduli space, on the moduli problem for these varieties, and they behave very well in the setting of deformation of moduli space. Yeah. So this so therefore one can apply again this results of Verbitsky, ergodicity, to conclude once you have one case of this hyperkahler with a Lagrangian fibration, once you can show that it's dominable, for example, or if you can show that it has vanishing copiage metric, then everything, all deformation class of this manifold, all, you know, we talked about the called it the locally trivial, okay, deformation. All hyperkahlers which are in the same locally locally trivial deformation class using ergodicity would also satisfy vanishing copiage metric. Okay. So to get vanishing copiage, one ideal way is to have dominable maps. And in fact, for dominable maps, the last section, I want to focus on 2 dimensions and maybe do some geometry, but so yes, the standing assumption in all of these theorems, let me say this lemma and theorem. This is the lemma of Matsushita, which is generalized by Christian Land and Kamanova in their paper to the setting of primitive symplectic varieties. That if you have a Lagrangian fibration from a projective symplectic or hyperkahler manifold, hyperkahler variety, then so if your vibration is only meromorphic in this sense, rational, okay, there exists a modification of your X into another Lagrangian fibred symplectic varieties, or hyperkahler variety, which may be singular, but with a morphism for the vibration. Okay. And this even though the hyperkahler variety that you end up with the Birational one may have singularities by well-known techniques of Matsushita. The singular part, the singular locus, do not dominate the base. Okay, so therefore the generic fibers are abelian varieties. Okay, so the generic fibers are the generic fibers of Lagrangian vibrations are. So this implies these Lagrangian subvarieties are these Lagrangian subvarieties are dominable. But you actually want to conclude the entire variety is dominable. And how do you do that? Well, either you show, so this is a strategy of Kamenova and Len. Either you show that there exists a double fibration, a transversal Lagrangian, two Lagrangian vibrations which are transversal. Okay, in that case, I already said how to do this. You just space change by one of the fibers of one Lagrangian vibration, which is horizontal with respect to the other Lagrangian vibration, base change by that, and you get you repeat what I did in one dimension, right? So here, in higher dimension case, you have to do it. You used to exploit the notion of neural model in codimension 1. Okay, so you have to avoid codimension 2, but you can avoid codimension 2, okay, by result of buzzard, okay, which is not in my paper as buzzard, but by later result buffers. For example, for projected space, you can avoid codimension, arbitrary codimension 2 subsets, okay, even neighborhoods of them, okay, by dominability. So when you can do that, you pull back by the complement, okay, because the complement of these codimension subsets don't matter. You pull back that Cn. Cn is Stein, okay, by the same theory. That will work. Okay, so Lagrangian subvarieties varieties are dominable, and to get the fact that so their theorem, this is Kamenova and Len basic theorem. So B2 greater or equals to 5, X Lagrangian subvarieties, and XYZ assume they assume the meromorphic or rational SYZ conjecture. So given a line bundle with square 0 and so on, you want to say that it actually gives rise to a rational Lagrangian vibration. That's the rational SYZ conjecture, some sort of abundance. Then they show that there exists a Lagrangian vibration, which is not almost holomorphic. When something's almost holomorphic, the general fiber is well defined, and it's so almost holomorphic implies fibers, general fiber are abelian, okay, right? Are smooth. Okay. The general fiber, because it's actually the fibers are defined, so the fibers are smooth, and therefore they're abelian, right? Because they're all Lagrangian subvarieties. Okay, which is not almost holomorphic, or there exists two, which are transversal. So we have two which are transversal, two almost holomorphic ones. We have two which are transversal. That implies by the argument you pull back, by the base change, by the abelian variety dominating the base, you pull back by that base change, and then that would give you dominable. Implies X dominable. So this implies, of course, that the Kobayashi metric of X is identically vanishing. But in this case, when you have something which is not almost holomorphic, then this implies by cycle space, by a series of cycle spaces, that the fibers. So in I didn't write down that lemma. I should have written down this lemma. This implies that the cyclospace by cyclospace it's Lagrangian, it's connected. X is connected, generically connected by abelian subvarieties, okay, which are Lagrangian. Okay. So it's generically fibred by Lagrangian subvarieties, which are abelian subvarieties, and rational curves. Okay. So the rational curves are horizontal sections which are rationally connected, okay, or uniruled, and there may be several sections which are uniruled, and they put together they can connect all the generic fibers, okay, by rational curves. So that implies dx is identically 0 again. Okay. So that's how they did this. Once you know that there exists something such a Lagrangian fibration, dx of that Lagrangian fibration is 0, and therefore by Gausselicity again they can conclude that all deformation classes, all Lagrangian hyperkahler varieties, which are in the same deformation classes as this, would vanish, right, using the same argument as ergodicity. Yeah, maybe I should stop here.
Any question?
Yes. For every hyperkahler which is deformation equivalent to one that has this property. Okay, assuming again this, right? So for all known hyperkahler manifold, these two are satisfied. Okay. So that's why we can claim that the result is true for all known hyperkahler. In fact, if you just do it by hand, okay, you know, Hilbert schemes, the hyperkahler manifold, the known ones are Hilbert schemes or generalized Kummer, or the O'Grady ones. Okay? They're all related to case 3, some construction from case 3. And you can do it by hand. Just those construction gives you directly dominable, gives you directly it's very simple exercise. They're all directly dominable. And they all have vanishing coefficients. They have everything, every antihyperbolicity product imaginable. Okay, right away. Except for general case 3. So if you know the case 3 surface downstairs is dominable, okay, then it will be you by just directly by hand you can prove that is the Hilbert scheme construction, all the other construction is dominable. Okay, but for case 3, which is we don't know which is dominable, we still don't know. Okay? Which is not elliptic, for example, we don't know.
In this setting, it's still true that meromorphic dominable implies dominable?
Yes, in this setting, meromorphic dominable implies dominable because you can always avoid coordination 2. So this is very easy if your base manifold, if you know that the base manifold is projective space. If you don't, I'm not quite sure yet. Because the projective, you know, in the case of projection was treated clearly by Greg Buzzard in the paper, okay, for example. And the argument is, once you know the theory of pure like domain, these arguments are pretty standard. And for the abelian varieties, that once it's as long, I mean, for abelian variety, you take a finite number of points, you can always make those points inside some lattice, and you know how to avoid those lattices. Okay. So same argument applies. giving complex threefold with elliptic vibration over a surface. Yes, yes. So exactly the same idea would apply. I mean, all whatever I did in for its buzzard works in higher dimensions. This is just one particular case, the hyperkahler. Yeah, I didn't treat those cases, but yeah, those cases works. So in that case, the base is an orbital pair. As long as the orbital pair base has is special, then you would.
So you only need the neuron model in codimension 1. You don't. I mean,
You only need a neural model in codimension 1 because you can avoid codimension 2, right? Because once so Cn, you can embed Cn, okay, into some universal cover that avoids codimension 2. Okay, so you pull back by Cn, then this is Stein. The base would be Stein in that case, right? And you do it exactly the same argument.
There are no further questions. Well, let's thank Stephen again. Thank you. And we resume at half.
So please remain seated. We'll take a group photo instead. Yeah. So maybe 3 minutes. Let me see whether our photo man is already there.